Okay, so I'm back, everybody. It's happy Thursday night. Okay, here we're looking at point 0.4 at the very bottom. We've got 0.6 a little bit, 3 meters off the bottom. And then we've got 0.7, which is 9 meters at the bottom. And the question is, what happens at 0.7? All right, so at 0.7, well, the cart isn't going to get any further, okay? Keep in mind, our force of friction is equal to 1,120 newtons, okay? It's not going anywhere past there, all right? It has to go back down. It starts to roll back down. That's fine. It goes, it starts going back down the other direction. What I'd like to know is, what is the minimum angle? Is it minimum? Maximum? Minimum? Yeah. Minimum. We'll discuss whether it's minimum or maximum in a second. What is the whatever? Let's do quote unquote minimum angle for the track. Okay, what is the minimum angle for the track so that the driving force of gravity overcomes the frictional force? In other words, frictional force. Okay, so we've got our cart going back down, and it's going to keep going back and forth, but there's a point where we're going to have the cart in such a way, there's going to be some angle such that the force of friction and the normal force here, force normal, we've got mg pulling straight down. And then we can break mg up into its components. And then, of course, that's theta. Okay. So we need the force of gravity to overcome the frictional force. Well, the frictional force, whatever it is, then has to be greater. Is that right? Let me think about this. It has to be greater than mg sine theta. All right? So, if it is greater than mg sine theta, then you're not going anywhere, okay? As soon as that happens, you're not going anywhere. So let's solve this for our frictional force, which we know to be 1,120 newtons, okay? So, so there's that. So what does our angle have to be? Theta, let's, I'm going to put mg sine. I always like to have the thing I'm solving for on the left. So, and I'm tired, so let's do it. Sine of theta has to be less than our force of friction over mg. And then, so theta has to be, theta has to be less than the arc sine of our force of friction over mg. And there's numbers for those. What is mg? Let's do that. mg is 4,900 newtons. So we're going to come over here and we're going to say that that equals the arc sine of 1120 over 4,900. So that means that theta is going to be less than 13.2 degrees. Okay, so is that a minimum or a maximum? I don't know. I don't even know if I have this going in the right direction. If theta is less than 13.2 degrees, then friction overcomes gravity, and it's really the maximum angle. It's the maximum angle for the track. So that, oh no, we want gravity to overcome friction. Okay, yeah, I did it right. And anything less than 13.2 doesn't work. Okay, so where's 13.2 degrees? I don't know. Let's just say it's here. Okay, so this is the point anywhere in this region here. From that point, and we could even let's forget that that's 0.6. Let's name this the opposite of our 50 or 13.2 degrees. We'll come up here and we'll put our point there. So basically our cart is going to stop somewhere in that blue region. Okay? So the cart will come in and it'll either roll in this way and come to a stop, or it'll keep going and come to a stop. This would be the furthest that it would get. If it happened to be just perfectly set up, okay, it would get all the way to here, right? That would be the max. What if we're back at our force of friction? So what if our force of friction is actually back to the 125 newtons that we started with? What's our angle then? Well, our angle is going to be less than the arc sine of 125 over 4,900, which equals 1.45 degrees. So at that point, let's come back to 1.45 degrees. That's really small. And I can't erase those blues, the blue stuff. How do I override blue here? What color should I use? Yellow? Ooh. All right. In this region is where you would stop, somewhere in that region, if from there to there, if the frictional force was 125, okay? Now, 125. All right. This is also saying that we really started out with a potential energy that wasn't so great that it would get us past the hump, right? So we're actually limiting ourselves to this maximum potential energy, okay? So you can figure out what that is if you want to, but somewhere in this realm, we're going to be stuck in there if our frictional force is 1.25, and if our frictional force is 1120, we'd be stuck in a little bit wider range, okay? So that's where the roller coaster would stop. Okay, this leads us, and this whole thing is going to be called stability. I'm going to call this whole thing, this whole video, stability. So let's do a little bit of talking about stability. I need to change that color to blue because yellow is not going to work for me. So let's say we have some energy. And we'll go up from there on both sides. And this is our energy. This is really a potential energy diagram because we're looking at the potential energies that we could have. We're going to say that our total mechanical energy is here. So we're going to start out with that much potential energy. Total mechanical energy equals our KE plus U. Where's our KE going to be the most? Right here. Okay, maximum kinetic energy. Where's our potential energy going to be the most? Right here and right here. Okay, so this would, if we call this the X dimension, then this would be X max plus X max. Down here is our minus X max. Here we'll say is X equals 0 or X naught. And without friction, and we let something loose here to roll back and forth without friction, of course, our energy total is going to equal our total mechanical energy. Total mechanical energy. That'll be a constant. Okay. With friction, however, we're going to end up finding, depending on the amount of friction and all that stuff, we're going to find ourselves in a smaller region eventually with zero velocity. We'll be down in there with some zero velocity stuck, right? In here somewhere. Okay, I don't want those things there. All right. Okay. There's another way you could think about this, and that is in Hooke's law, we have some spring hooked up to a box that slides on a table, and its position when it finally stops is going to be not far, like if this is minus X max and this is plus X max, our position where it finally stops is going to be just some slight small difference from our equilibrium. Just this little bit of difference right there. Okay, so in the book, there's a figure. Figure 8.13. And there's an example. That figure is an example of a potential energy well. It resembles the Higgs boson potential energy well. So let me draw it. So go look up figure 18.3, and I'm going to draw, oh boy, it's so much harder to do without, that's just ridiculous. That was terrible. Better. Okay. Here's our absolute bottom. Here's a point of inflection, an inflection point. Here's an inflection point. Here's an inflection point. And then we're going to give our total mechanical energy for the system, we're going to make it this much. Okay? So if we were to start out with no friction, our ball, our cart or whatever it is, would go this direction, and it would go all the way over the hump like that, and then it would come back up to this side with no friction. It would get to this point, go to v equals 0, and turn around and go back down the other way. Okay? So that's what would happen without friction. But what about with friction? Well, I don't even know if we want to talk about with friction yet. Let's talk about more about these regions. Here. So this region is what we would call stable. Okay? Same thing goes over here. So we've got two stable regions. This region in the middle here is unstable. In fact, if you did it just right, you could put your object right here. I didn't do a good job drawing this curve. But just like the roller coaster on top of the hill, it's not moving until the wind just slightly blows it. So here you are at the top, everything's symmetry. You're sitting there, you could go either way, but you're gonna need a little bump, all right? You get this little tiny gust of wind or whatever, and the next thing you know, you're either going this way or you're going that way, okay? So this is called unstable region, even though you could possibly be sitting right there, okay? So yes, unstable. We've got our stable regions, we've got our unstable region. Now, that's if our total mechanical energy is this much, okay? So if our total mechanical energy is this high right here, this is where we are allowed to be in this range. Stable and unstable, okay? So in other words, I could take and place the ball right there, and it would want to stay there until it got bumped. And then once it gets bumped, then it will find itself in either this region or this region. If we use this as our total mechanical energy, The ball will still prefer to be in these stable regions, okay, but it will oscillate back and forth. But if there's friction involved, you're going to find that that thing ends up, just like we figured out before, in the bottoms of the wells. Okay, we call these wells. Now, there's these things, points. Do I want to get into that yet? I don't know. Are we going to do that? No. This point, I'm just going to say a couple of things. This point and this point, this is Q, this is minus Q. They're just points, okay? They're the, what do I want to call them? They're the points around which the equilibrium is found. Your stability is found. This potential U of X, there's all kinds of, you could do it many different ways. I'm going to call this one 2 times x to the 4 minus x squared. That's what we get. Okay, so, and you can go through and figure out what all the inflection points are and all the turning points and blah, blah, blah. You can do all that stuff if you want to. So here we are with what we just looked at, stability. Oh boy. Stability cases. So, stable equilibrium. That looks something like this. Here's our little ball in the bottom, and this is our total mechanical energy, and anywhere from here to here, we are in a stable equilibrium position, okay? Especially here, all right? That means that our V is either equal to a constant or 0, and in our case, V is going to equal to 0, okay, in this situation. All right, not V is equal to a constant because it's going to come down and sit here. We're going to think about this with friction. And we already just discussed that, is the ball going to sit exactly perfectly on the bottom? Chances are no, right? The chances are you're not going to find it exactly at the bottom. It'll be somewhere off the center, but won't be moving because its velocity will equal 0. All right. Any bump, any slight bump to this little guy, in other words, something that gives it some energy that's been added to it, any little bump, all it will do simply or just makes it oscillate a little bit, right? Oscillate. That's it. And since we have friction, it's going to oscillate a little bit and then come to rest. Okay? So that's stable equilibrium. What about unstable equilibrium? Well, that looks something like this. We'll place our ball at the very top. Somewhere here is our total mechanical energy. And we've placed it there, meaning that all, you know what? I can't put the total mechanical energy there. I have to put the total mechanical energy at the center of mass of this thing. Okay, so it runs right through the center of mass, that total mechanical energy. It's going to sit there. It's perfect. Everything's going to happen. However, any bump makes it accelerate. And of course, we're talking, the reason why is because G is pulling down, right? So it's going to accelerate. And if we don't think about terminal velocity, it will just continue to accelerate, right? A force acting on something without friction is going to give us acceleration immensely or infinitely. But with friction, which is what we're talking about, it'll accelerate to a terminal velocity. All right, that's unstable equilibrium. Then we have neutral equilibrium, and I'm hoping that you guys can guess what that looks like. That looks like a line, a flat surface, right? And the ball is placed in that flat surface. The total mechanical energy is exactly at the center of mass. Any little bump will make it obtain, we'll give it, let's do give instead. Give it a constant v. All right, so it'll have a constant velocity. Without friction, that constant velocity will stay, right? You've just given it some kinetic energy. With that little bump, you gave it some kinetic energy, and it will maintain that constant velocity forever. However, we're talking about with friction, so what's going to happen with friction? It'll have a constant velocity that only decreases to 0. Okay? So we've got stable equilibrium, unstable equilibrium, and neutral equilibrium. You'll need to know those for the tests. So that pretty much kills everything. I just want to make sure we don't have any leftover concepts that need to be elucidated, brought to light. Oh, heck. I do have more to talk about. All right, guys, I've got more to talk about. I'm going to kill this. We're going to start talking about conservative versus non-conservative forces.